Hello, welcome. In this video series, we're going to go over section 3.4 from the Lock 5 textbook, Bootstrap Confidence Intervals Using Percentiles. So the outline for what we're going to cover in the next couple videos would be confidence intervals based on Bootstrap percentiles. We'll go over how to do this in StatKey. You are getting different levels of confidence for confidence intervals, impact of sample size and level of confidence on the interval width. How do these change the size of your confidence interval? And then looking at a couple of cautions. Okay, so let's begin. So first review, a bootstrap distribution is shown below right here. We got a bootstrap sampling distribution. What does each dot represent? Is it one data point, one bootstrap statistic, n data values, or 1,000 bootstrap statistics? I hope you remember this from the last couple of classes or sections. That is one bootstrap statistic. So each of these dots, it comes from a bootstrap sample, and they plot the statistic, whether it's a p-hat proportion or a mean or a correlation. Okay, the first thing I want to look at is body temperature. So we've got some data in StatKey. I'm going to go to StatKey in a couple minutes here. First, let's just look at a screenshot. So we're looking at a data set, original samples to the right, of a sample of 50 people, took their body temperature, got a sample mean of 98.26, median of 98.2, standard deviation of 0.765. And then here there's a bootstrap sample distribution, 1,000 different bootstrap samples, to get a mean of 98.262. That should be very close to the sample mean, and a standard deviation of 0.105. And remember, this standard deviation right here is also called the standard error. Standard error is the standard deviation of the sample distribution. So on the side here, we're going to go through how would we compute a 95% confidence interval. We're going to take the sample mean, which is 98.26, and we're going to add and subtract 2 times the standard error. And the standard error is the standard deviation of sampling distribution. So add and subtract 2 times 0.105, and we get a lower bound of 98.05, and then add this 0.21 to get an upper bound of 98.47. And for a summary, we would say we are 98% sure, or we could say we are 98% confident that the average body temperature for humans is between 98.05 degrees and 98.47 degrees. So notice where that 98.6 come from? It's not in our range. So this would provide some evidence that 98.6 is not the true population parameter or the true population temperature average. All right, so we're going to go in this section. Again, that's kind of review what we did in the last section. But what if we want to get other levels of confidence? Suppose we want to be have a higher confidence than 95%, such as a 99% confidence interval. How would we compute that? What exactly does that mean? So the percentile method, that's the new material in section 3.4. If the bootstrap distribution is approximately symmetric, so we need this to be true. We'll look at some examples later on these slides, if that's not the case. But if we have a nice symmetric bell-shaped distribution, we can construct a confidence interval by finding the percentiles in the bootstrap distribution so that the proportion of bootstrap statistics between the percentiles matches the desired confidence level. Okay, so that's a lot of verbiage. Let's look at an example. Oh, first let's do a diagram, excuse me. So say, we have thousands and thousands of samples. Ideally, it would look more and more like this normal or symmetric bell-shaped curve. And again, don't forget the center is going to come from the statistic, the sample statistic. And if we want to get a p%, like 99%, we want the exact middle p%. And the idea is we're trying to figure out these two cutoffs right here. So the lower bound and upper bound, these two cutoffs are going to be our confidence interval for a 99 or 95 or 90% confidence interval. So keep in mind, whatever percent confident we want to be, that's going to be the middle of the sampling distribution. So we want to keep the middle p%. We want a p% confidence interval. So if we think about a 99% confidence interval, there's 1% left over, but we're going to split that up in each of those two tails, so they each get half of a percent, or 0.05. So one way to think about it is this 99% confidence interval would be the 0.5th percentile. This is the bottom percentile, and then 99.5 percentile. And these percentiles refer to this Bootstrap distribution. So let's go back to that body temperature example. And I'm going to go through this in a second with stat key. And so we have the sample right here. Again, the mean of this, 98.26. If we take enough samples, I'm going to suggest 2,000 instead of 1,000. The mean should be pretty close to the sample mean. And what we're going to do is click on this two tail and then make sure the center is the percentage that we want. And we get the middle 99% of this Bootstrap. So down here at the bottom, I get 97.996 and 98.584. So what I want to do is I want to look at this example, but in stat key. So if we are in stat key, we're looking at Bootstrap confidence intervals, is chapter 3, and I'm going to go to confidence interval for a single mean. And this is a prepackaged data set, so I'm going to click over here and look for body temperature, body temp 50. Click on that, and notice here we have the mean of 98.26, sample size of 50, standard deviation of 0.765. So I'm going to generate 2,000. 2,000 samples. The 2,000 samples are all Bootstrap. So if I click on a dot over here, notice on the bottom right, this Bootstrap sample changes. We have a very extreme Bootstrap sample, but most of them are kind of slightly towards the middle. So if I want to construct a 99% confidence interval, I'm going to click on two tail. And the center spot is always initially going to start at 95%. Click there, and then we're going to change proportion to 0.99. I'm going to click OK. So that gives us a 99%. And notice we get a nice visual. What this does is this separates the middle 99%, or 99% roughly, of these dots, of these 1,000 Bootstrap samples. And the cutoff is 98.001 at the bottom, and then 98.541 at the top. So what I'm going to do is, let's restart this. Let's reset the plot. Let's generate another 2,000 samples. So I have another 2,000 Bootstrap samples. Click on two tail and click the center, make that 0.99, and then click OK. And notice right here I have 97.986. Last time this was 98.001 and then 98.534. So this Bootstrap method, since all these Bootstraps are done randomly, StatKey is doing this sampling with replacement randomly, just 1,000 times very quickly. There's not going to be an exactly correct answer that the entire class will get, even with the same percentage. But they shouldn't be too far off. 98.001 is not too different from 97.986. And then notice right here, the prepackaged screenshot was the 97.996. So pretty close to what we got, but not exactly the same thing. All right, so which is wider, a 90% confidence interval or a 95% confidence interval? That's all we know. And think about the sampling distribution, how we would cut that off. Hopefully you guessed 95%. If we take 95% confidence contains the middle 95%, which is more than the middle 90%. So the bigger the confidence level, then the larger the range is going to be. Okay, let's go through one more example in StatKey. And we're looking at the correlation in Florida lakes between mercury level in fish taken from the lake, and acidity. So there's a connection between acidity of the lake and the mercury in the fish. And we have a scatter plot shown right here of the data of the sample given. This is from a sample from 1993. And the correlation value, Pearson's R, is minus 0.575. So there's a negative correlation, not too strong. Suppose we want to get a 90% confidence interval for rho. Again, this letter is rho, RHO, a Greek letter, and that's the population way to write correlation. So I'm going to go on StatKey in a second, but we have a screenshot. We've got the original sample on the top with the original R, 0.575. Same as before, we're going to click on two-tail and then make that center 0.900. And then at the bottom right here, that gives us our two confidence levels, or our confidence bounds, minus 0.702 to minus 0.433. So we would say we are 90% confident that the true correlation between average mercury level and pH of Florida lakes is between these two values. Okay, so what I want to do is I want to go through this a couple times in StatKey. So we're doing confidence interval for correlation. So I'm going to click on StatKey to start over. And I'm looking at Bootstrap confidence intervals. I'm going to click confidence interval for slope correlation. And we have the prepackaged Florida lakes mercury as function of pH. I've got my original sample right here, the slope of minus 0.575. Excuse me, no, not the slope, the correlation, minus 0.575. All right, I'm going to generate 2,000 Bootstrap samples. Just click 1,000 twice. I have 2,000 samples. I have my standard error here, so I could use this to get a 95% confidence interval. But recall, we want to get 90%. So to get 90%, I'm going to click on two-tail, and then I'm going to change this center entry to 0.90, or just 0.9. Click OK, and I get a minus 0.706 to minus 0.433 as my confidence interval. So right here, this is my 90% confidence interval. So before we break on this video, excuse me, I wanted to look at that slide again. Just to see we don't get the exact same thing. I got minus 0.702 to minus 0.433. This is a different Bootstrap sampling distribution with 3,000 samples, but it is pretty close to what we got on StatKey.